Welcome to Harryverse. Tonight, we are diving into one of the strangest stories in our sky, what the James Webb Space Telescope and other observatories are really seeing at 3i Atlas. If you enjoy these deep, slow explorations of cosmic mysteries, please like the video, subscribe to Harryverse, and share it with someone who loves space as much as you do. Thank you for choosing to spend your time here. It really helps this channel grow and tells us to keep making long, detailed investigations like this one. I am very curious about you as well. What time are you listening to this, and where in the world are you right now? Let me know in the comments. I would love to see where Harryverse is traveling tonight. Now, let us begin. On a clear January night, in the late 2020s, the stream of raw data arriving from spacecraft around the sun carries a quiet but profound change. The calendar reads January 22nd, 2026. Yet the light that makes this change visible left the vicinity of the sun days before, when an interstellar visitor called 3i Atlas was already past its closest approach. For months, telescopes on Earth and in orbit have watched this object sweep through the inner system, treating it at first as another fast-moving icy body on a hyperbolic path. It is cataloged, tracked, fed into orbital prediction software, and lined up with previous examples of interstellar debris. Only when the Solar and Heliospheric Observatory, a joint mission of space agencies designed to monitor the space around the sun, delivers its latest processed images, does it become clear that 3i Atlas is not behaving like a simple fragment of ice and dust. A feature emerges that ground-based telescopes could not resolve a faint envelope of scattered ultraviolet light that reveals the presence of neutral hydrogen on a vast scale. The all-sky Lyman Alpha camera aboard the observatory is sensitive to a particular wavelength of light emitted when hydrogen atoms are illuminated and stripped of their electrons by solar radiation. Around 3i Atlas, this instrument now records a concentrated plume of hydrogen that blossoms outward far larger than the visible coma and tail seen in optical images. This plume does not appear at perihelion itself, but rises sharply roughly 9 days after the object swings around the sun on October 29, 2025. From that moment, it is tracked continuously for more than 30 days, forming a moving cloud that appears to cling to the object and stream away at the same time. Analysts convert the brightness of this hydrogen into an estimate of how much water must be breaking apart to supply it. The numbers are unsettling. Over that short observation window alone, the implied release of water reaches roughly 13.5 million metric tons. That mass corresponds to thousands of large swimming pools of liquid, except that here the water is frozen, sublimated, and then torn apart into hydrogen and oxygen by solar ultraviolet light. In a little more than a month, this much material leaves the surface or near-surface layers of 3i Atlas and disperses into interplanetary space. On ordinary comets, outgassing close to the sun is expected. As ice warms, it turns directly to vapor and carries dust grains away, driving the familiar jets and tails. In that standard picture, the outflow is messy, governed by fractures in the ice by rotation and by the pattern of sunlight over an irregular surface. Hydrogen may be present, but it is simply one more product of solar heating. In the case of 3i Atlas, however, the new hydrogen plume forces a more careful accounting. The sheer volume of water implied by the observations shows that this object is not just a dry rock with a thin veneer of ice. It is a rich reservoir, a body with enough volatile material to sustain high levels of mass loss without quickly exhausting itself. In rocketry, water is more than a volatile. It is a potential fuel. Through a process called electrolysis, water can be split into hydrogen and oxygen using energy from a power source. When recombined in a controlled burn, these gases form one of the most efficient chemical propellant pairs known, capable of producing high exhaust velocities and strong thrust. A technological civilization faced with the problem of traveling between stars would quickly discover that carrying all of its reaction mass from its home world is inefficient. Each kilogram of fuel lifted out of a deep gravitational field costs more fuel. A more elegant strategy is to harvest resources in space. Ice-rich bodies become refueling sites, mobile depots of potential propellant that can be tapped and then abandoned. When looked at through this lens, the hydrogen plume around 3I Atlas begins to acquire a different meaning. Instead of a passive byproduct of sunlight on an untouched surface, it starts to resemble the signature of fuel being liberated and potentially prepared for use. The timescale is suggestive. The plume appears after perihelion, not before, and remains strong as the object recedes from the most intense heat. The rate of release inferred from the data is high enough that, if directed, it could deliver sustained thrust over many days. For an object already traveling at more than 60 kilometers per second relative to the Sun, even modest additional pushes can have significant effects on its eventual path. The hydrogen detected by the Solar and Heliospheric Observatory represents precisely the kind of material that a hitchhiking spacecraft or an embedded vehicle would exploit. If an engineered system is present either attached to the surface or buried within it, might use water from the surrounding ice as both shield and fuel, splitting it into hydrogen for propellant and venting it through outlets that are invisible at the resolution of current imaging. In such a scenario, the difference between a natural plume and a controlled exhaust lies not in the gross amount of gas, but in the hidden order of its flow and timing. At this stage, the data do not prove design. They show only that 3I Atlas is shedding stupendous quantities of water, enough to support the idea that it could serve as a propellant tank for any technology capable of tapping it. Yet this alone already distinguishes it from previous interstellar objects, many of which appeared comparatively inert or displayed more modest activity. 3I Atlas is large, fast, and now clearly rich in accessible volatiles. In the analysis rooms where these plots and images are examined, the story of this object quietly shifts. It is no longer just a messenger from another star system sweeping through on a one-time visit. It becomes, at least in principle, a vehicle or a depot, a moving concentration of resources in an interstellar desert. The hydrogen plume, seen in ultraviolet light, is the opening signal in that shift. It is the first clear indication that this body carries not only information about its birth environment, but also the raw ingredients for motion, for steering, and perhaps for something that crosses the line between geology and engineering. As further observatories, including the James Webb Space Telescope, turn their attention to this target, the hydrogen cloud serves as both a beacon and a puzzle. It says that something powerful is happening just beyond the limits of current resolution, and it invites a closer look at how a seemingly anonymous object has suddenly become central to questions about how any civilization might choose to cross the space between stars. In the days after the hydrogen plume around 3, I-Atlas is confirmed, attention turns to what that much water actually means for motion in space. In ordinary astronomical reports, ice loss from a comet is treated as an incidental detail, something to be modeled so that brightness changes do not confuse size estimates. In astrodynamics and propulsion studies, however, mass that can be thrown away in a controlled manner is not an incidental detail at all. It is the central ingredient of any engine that relies on reaction mass. A rocket, whether chemical, nuclear, or something more exotic, moves by expelling matter in one direction, so that the vehicle is pushed in the opposite direction. Every kilogram of gas that leaves a body at high speed provides a small push. Over time and with enough mass, these pushes accumulate into meaningful changes in velocity and path. When analysts tally the 13.5 million metric tons of water released by 3I-Atlas during the initial observation window, they are not simply counting evaporation. They are perhaps reluctantly counting potential thrust. If that water is merely drifting away from random fissures on a warming surface, it contributes only chaotic nudges that can be absorbed into standard comet models. If instead, some fraction of it is being channeled through specific vents at specific times, it becomes the exhaust of an engine that no one has designed on Earth. This distinction lies at the core of what some researchers quietly nickname the hitchhiking hypothesis. The idea is straightforward in its logic. A technological civilization that has solved the problem of building machines can attach those machines to naturally occurring bodies, rather than constructing entire starships from the ground up. Instead of lifting huge propellant tanks out of a deep planetary gravity well, such a civilization can search its own system for ice-rich objects and mount hardware on them. Once that is done, the body itself becomes a transport platform. Its mass provides shielding against radiation and small impacts, and its volatile content becomes a store of reaction mass that can be tapped whenever steering is required. In this scheme, water is a standard currency. Through electrolysis, which breaks water into hydrogen and oxygen using electrical energy, the ice becomes fuel and oxidizer. On Earth, this combination already powers some of the most capable launch vehicles in history. The exhaust from hydrogen and oxygen combustion is hot water vapor, leaving minimal contamination and providing high efficiency. If the same process is applied on or within a comet, the surrounding space becomes both a fuel depot and a flight corridor. The hitchhiking approach also addresses a fundamental limitation known from classical rocketry. The more fuel a vehicle carries at launch, the more fuel it must spend just to move that fuel. This feedback is often called the tyranny of the rocket equation, a reminder that chemical rockets do not scale gently to interstellar distances. By contrast, a craft that can move from one resource-rich body to another and refuel along the way does not need to carry all of its mass from its origin. It can accelerate modestly, coast for long periods, and then harvest the next ice reservoir it encounters. In a galaxy filled with debris, this strategy is appealing. If even a small fraction of interstellar objects are as water-rich as 3I-Atlas, appears to be a network of stepping stones through the Milky Way begins to emerge. Against this backdrop, the specific numbers derived from the solar and heliospheric observatory data gain weight. The hydrogen plume is not a thin veil. It represents enough liberated water to sustain prolonged burns for a modestly sized vehicle, especially if that vehicle is patient and accepts slow cumulative changes rather than dramatic accelerations. An object that already enters a new star system at tens of kilometers per second does not need a large additional push to reshape its outbound path. A gentle but sustained thrust, applied near perihelion, when gravitational leverage is highest, can redirect its future journey by enormous distances over millions of kilometers. In the case of 3I Atlas, the observed timing of the plume beginning days after closest approach and persisting as the object climbs away from the sun suggests that whatever mechanism is releasing this water remains vigorous beyond the moment of peak heating. Thermal models of cometary behavior predict that outgassing should correlate closely with the intensity of sunlight received. As the object recedes and solar flux drops, the rate of sublimation is expected to fall in a predictable way. Yet, in the plotted hydrogen density, the decline is not as steep as these simple models anticipate. The plume maintains a surprising robustness, hinting that processes deeper within the body may be sustaining it. These processes could be purely natural. Phase changes and internal fractures might open new voids to the surface, and latent heat stored in layers below could keep ice vaporizing even as the outer shell cools. Gas may channel through fractures and vents in ways that mimic controlled flows without any design at all. The burden of proof remains on those who would invoke engineering, where physics alone might suffice. Still, the match between what is observed and what would be useful for a hitchhiker is difficult to ignore. A civilization that has mastered long-duration automation could embed drilling systems and power units inside a suitable cometary body. Radioisotope heaters, or compact fusion devices, could warm interior reservoirs, drive electrolysis units, and pressurize tanks of separated hydrogen. That hydrogen would then be fed to thrusters that open to the surface in the form of jets. Viewed from a distance, such jets would be indistinguishable from natural geysers of gas. Yet they would fire in sequences chosen to guide the host body along a desired path. Even if most of the mass loss is still uncontrolled sublimation, a relatively small fraction of directed flow could steer the whole structure using the bulk of the ice as expendable propellant. The hitchhiking hypothesis further posits that such an arrangement would not be a single-use device. Once an engineered system is installed, it could ride the same host from star to star, refueling whenever it passed near new ice fields or captured smaller bodies. Over timescales far beyond human history, this would create slow but persistent circulation of probes through the galactic disk. Each passage near a new star would be an opportunity to scan planets, map magnetic fields, or deposit smaller sensors. In this picture, 3I Atlas would not be an isolated curiosity, but one node in a vast, sparse network of migrating machines. For the moment, this remains a chain of reasoning anchored only loosely to the available data. The hydrogen plume could be entirely natural, a relic of the way the object formed around a distant star. Yet the fact that this water-rich body is now in the inner solar system, moving along a path that brushes close to major planets, invites speculation about use as well as origin. The 13.5 million tons of water detected in a single stretch of observation underline one simple conclusion. Whatever 3I Atlas is, it is not empty. It carries a stockpile of reaction mass that any competent propulsion system could exploit. As study of the plume continues And as other instruments begin to probe different wavelengths for signs of heat and composition, the idea that interstellar travel might be easier with such carriers than without them lingers in the background. 3I Atlas has already shown that the galaxy can send large, volatile, loaded objects between stars. The next question is whether any of them are riding under their own guidance or under guidance given long ago, rather than drifting entirely at the mercy of gravity and sunlight. As the magnitude of the hydrogen plume sinks in, the next question turns from inventory to behavior. A comet warmed by the sun is not a mystery in itself. Ice near the surface absorbs radiation molecules at the outermost layers, gain energy, and once they become mobile enough, they escape into space, dragging dust and fragments with them. For decades, astronomers have built and refined mathematical models that describe this process. When applied to a new object, these models predict how gas production should rise as the comet approaches perihelion peak near closest approach and then decline along a smooth curve as it recedes and cools. The shape of that curve depends on distance from the sun composition, rotation rate, and surface structure. It is not arbitrary. With 3I Atlas, those familiar expectations provide a baseline against which the new data can be compared. When researchers fit the observed hydrogen brightness to standard sublimation models, some parts of the curve behave as expected. The plume ramps up as the object comes in, showing that ice is indeed responding to increasing sunlight. But around the time shortly after perihelion and into the weeks that follow, discrepancies appear. The emission does not fall away as quickly as the simplest distance-based explanation would suggest. Instead, the density of hydrogen remains high for longer, and the rate at which it declines with distance does not match the textbook profile of a snowball simply receding into cooler space. In some reconstructions, there are hints of plateaus and changes in slope, as though the underlying engine producing gas has shifted states or tapped into new reservoirs not purely governed by surface temperature. These departures from the expected curve do not immediately announce technology. Many natural processes can produce complex outgassing patterns. Thermal waves can propagate inward through a porous body, causing delayed responses. Internal cavities can open suddenly, feeding brief surges of gas. Rotational changes can shift which regions receive more sunlight, altering the distribution of activity. All of these effects are known from previous comet studies. Yet the comparison between what is seen and what is predicted still matters. If the plume were purely the result of sunlight on an inert block of ice, its evolution should be tightly tied to solar distance and orientation. The degree to which it is not forces investigators to entertain additional energy sources or structural complexities inside 3I Atlas that go beyond the most conservative assumptions. At the same time as gas production is being scrutinized, another line of analysis unfolds in orbit determination teams. Every active comet experiences what are called non-gravitational accelerations. When gas and dust leave the nucleus at high speed, they impart a reaction force on the body, nudging it away from the path it would follow under gravity alone. Over many orbits, these small pushes can accumulate into substantial shifts. For short-span observations like those of 3I Atlas, they show up as tiny deviations between predicted positions based on gravity only, and the actual positions measured in the sky. To track any object reliably, astronomers maintain an ephemeris, a set of parameters that describe where it will be at any given time. For a new interstellar object, this ephemeris is updated frequently as new astrometric points arrive. In the case of 3I Atlas, the emergence of the hydrogen plume prompts a fresh round of calculations. If more than 10 million tons of material have been ejected in a matter of weeks, then by Newtonian mechanics, there must be some recoil. The direction and magnitude of that recoil depend on how the gas leaves the surface. If the activity is distributed irregularly with jets firing from random fractures, the net push may average out over a rotation and produce only a slight drift that can be folded into standard non-gravitational models. If, however, the venting is focused through specific regions in a stable pattern, the resulting acceleration can be more coherent, altering the object's trajectory in a way that has a preferred direction. That is the critical distinction between a melting snowball and a controlled engine. In one case, the gas escapes wherever the structure fails, and the cumulative effect is messy, but statistically predictable. In the other, the gas is expelled through what are effectively thrusters arranged and timed to guide the host body along a chosen route. When orbital computers ingest the latest measurements of 3I Atlas and attempt to fit them with a purely gravitational solution, subtle residuals begin to appear. These are the small discrepancies between where the models say the object should be and where it actually is. As non-gravitational terms are added to the equations to account for outgassing, some of these residuals shrink, but not all of them vanish cleanly. The fit improves, yet hints remain that the acceleration might not conform perfectly to the simple templates derived from typical comets. Here again, the data are not yet definitive. Measurement errors, incomplete sampling of the orbit, and limitations in the current understanding of 3I Atlas's shape and spin all complicate the picture. A slightly irregular nucleus or an unusual distribution of active regions could mimic what more exotic explanations would also produce. For this reason, most dynamicists adopt a cautious stance. They note the anomalies, adjust their models, and call for more observations. Still, for those looking at 3I Atlas through the lens of the hitchhiking idea, the combination of a sustained hydrogen plume and non-trivial non-gravitational accelerations is difficult to ignore. If a device buried within the body is deliberately venting propellant, it would naturally produce both. The same flow of gas that lights up in ultraviolet images would also push on the bulk of the object, changing its path. From the perspective of that hypothetical system, every kilogram of water is not just a source of hydrogen for future burns, but also a lever on its own trajectory. In the discussion rooms where these possibilities are weighed, a constant reminder hangs in the background. Extraordinary claims require strong support. Inferring any kind of engineered behavior from astronomical data is far beyond the usual scope of planetary science. The simplest models must always be tested and ruled out first. Yet there is another principle that sits alongside this caution. Scientific practice also demands that data not be forced to fit expectations. If repeated high-quality measurements continue to diverge from natural explanations, and if those divergences align with what would be useful in a technological context, it is at least legitimate to explore that connection as a working hypothesis. In that sense, the hydrogen plume becomes a kind of indicator, not of certainty, but of potential. It demonstrates that 3I Atlas has the capacity to play the role of fuel source depot or engine. It shows that the mass being ejected into space is sufficient to matter for its motion. Combined with the detection of a powerful hydrogen cloud, the recalculated ephemeris puts 3I Atlas in a new category. It is no longer just a messenger from another system carrying clues about its own formation. It is also a test of how far current instruments can go in distinguishing between a natural object undergoing complex physical changes and a structure that might be using those same physical processes as part of a purposeful journey. In the months that follow, every new measurement of its position, every refinement of its orbit, and every additional glimpse of its outgassing pattern contributes to this unfolding experiment. The question slowly shifts from whether 3I Atlas is active to what kind of activity best explains the way it moves, and whether the solar system is watching a snowball in sunlight or something that has learned to treat water and hydrogen as tools rather than as accidents. While gas production curves and non-gravitational accelerations are being examined, another feature of 3I Atlas begins to draw quiet attention in the orbital dynamics community. It is not a new measurement, so much as a rereading of something that has been known since the object was first tracked, a parameter that initially seemed unremarkable, but in the light of the hydrogen plume and the hitchhiking idea becomes harder to dismiss. This feature is the inclination of the trajectory, the angle at which 3I Atlas slices through the orbital plane of the planets. The solar system is not a random swarm of bodies moving in all directions. Most of its mass lies in a flattened disk, the ecliptic plane defined by the path of Earth around the Sun and approximately shared by the other major planets. Asteroids and comets that formed within this system tend to orbit near this plane with modest tilts caused by past interactions. By contrast, interstellar visitors are expected to arrive from arbitrary directions. In the larger frame of the galaxy, there is no reason for debris ejected from one distant star to prefer the thin disk of another. Their velocities are set by events that happened far away and long ago. When these objects cross the Sun's sphere of influence, the expectation is that their incoming paths will be scattered across a wide range of angles with respect to the ecliptic. Some will pass through close to the planetary plane by coincidence, but many will approach from steep angles above or below, tracing out trajectories that intersect the solar system like needles at random orientations through a flat sheet. Against this background, the measured inclination of 3I Atlas stands out. Detailed fits to its path show that the trajectory is tilted by only a few degrees relative to the orbital plane of the planets, an angle small enough that, drawn to scale the incoming path, nearly overlays the ecliptic itself. In practical terms, the object does not dive steeply through the disk. It slides into it, traveling in a direction that remains close to the same broad plane where Earth, Jupiter, and the other worlds circle the Sun. For natural interstellar debris, such an alignment is not forbidden. Random processes can produce any angle. Yet the probability of an object from another system happening to approach with such a low inclination is lower than the probability of it arriving at a more tilted angle. Each new interstellar object that is discovered offers a chance to test this expectation. If most of them show high inclinations, the assumption of random arrival directions holds. If several show low inclinations, questions arise about selection effects and in more speculative discussions about guidance. In the case of 3i Atlas, the small inclination becomes more than a dry number because of what it enables within the solar system. A path that hugs the planetary plane is dynamically convenient. It offers multiple opportunities for close passages by major planets, whose orbits also lie near the ecliptic. These encounters can be used to exchange energy and angular momentum with the planets through gravity. Assists a technique long used by human-built spacecraft to gain speed or redirect their paths without expending large amounts of propellant. When a craft approaches a planet along an orbit that lies roughly in the same plane, it can skim through the planet's sphere of influence, and depending on the geometry, emerge in a new direction or with a different velocity relative to the Sun. By choosing paths that move from one planetary encounter to another, mission designers on Earth have sent probes on complex tours of the outer solar system, past Jupiter, Saturn, Uranus, and Neptune, and out into interstellar space. All of these maneuvers start with the simple fact that the planets occupy a disk-like region. A trajectory close to that disk offers more options than one that cuts across it at a steep angle. For 3i Atlas, the near alignment with the ecliptic plane means that during its brief passage through the inner system, it comes into meaningful proximity with several planets. Not all of these passes are close enough to produce dramatic deviations in its orbit, but they mark potential nodes in a network of possibilities. If any device loaded on or within the object wishes to survey planets, release probes, or adjust course using gravity assist, such an orbit provides a favorable platform. The small inclination thus looks in hindsight like the choice an engineer might make if given the task of sending a carrier through the solar system with minimal fuel costs and maximum access to the worlds of interest. A highly inclined path that plunges far above and below the ecliptic would visit the Sun, but remain dynamically distant from the main planets, requiring much larger energy expenditures to change direction or to rendezvous with any specific target. A low inclination path, by contrast, offers repeated chances to interact with the massive bodies that dominate local gravity. When orbital analysts plot the incoming corridor of 3i Atlas in 3 dimensions, highlighting the plane of the planets in the line of nodes where the trajectory crosses it, the geometry has a stark simplicity. From far out in interstellar space, the object approaches along a direction that brings it into the solar system's disk, almost as if it has been threaded into that narrow band. It does not meander through the outer halo at a steep tilt. It comes in already aligned, requiring only small adjustments, if any, to convert its path into one that can exploit planetary gravity. In a purely natural interpretation, this is an example of how even low-probability configurations will appear occasionally in a large universe. Given enough time and enough objects, some will arrive on low-inclination trajectories, just as some will arrive on high-inclination ones. Observers must be careful not to overinterpret a single case. The statistical argument is subtle. One object is not a distribution. Yet when that single object also shows unusual outgassing behavior and a powerful hydrogen plume, the alignment begins to feel less like an isolated coincidence and more like part of a pattern of anomalies. Each feature by itself may fit within natural variance. Together, they begin to form a list. It is in this context that some theorists extend the hitchhiking hypothesis from an abstract idea to a concrete scenario for 3i Atlas. In their view, an artificial intelligence or automated navigation system embedded in or attached to an ice-rich body in another star system could over many orbits engineer a departure path that ejects the carrier object into interstellar space on a curated trajectory. By using gravitational interactions with its own system's giant planets, such a system could preferentially send the body toward regions of the galaxy that intersect the planetary planes of other stars, rather than aimlessly into the sparse halo. This would maximize the chance that when the object eventually arrives at another system, it will pass through the disk plane where planets are likely to orbit as opposed to diving through empty polar regions. The alignment of 3I Atlas with the solar ecliptic would thus not be an accident, but the result of a long chain of subtle navigational steps, taken long before it entered the sun's influence. At present, this remains an untested story, layered on top of solid but limited data. Observers can say with confidence that the inclination is low. They can say that such an orbit is dynamically well suited to planetary encounters. They cannot yet say why it is low. Gravitational nudges from other bodies in the past, random encounters in its birth system, or biases in how such objects are ejected into interstellar space could all play roles. A natural explanation is always available and must be taken seriously. Nevertheless, the fact stands that 3I Atlas has arrived on a path that an experienced mission planner would recognize as efficient. It passes near the sun in the same general plane where the planets move. It offers multiple opportunities for gravity assists. It does so while shedding enormous quantities of water that could serve as fuel. Each of these features taken alone could be dismissed as a curiosity. Taken together, they nudge the narrative away from a purely passive visitor and toward the more unsettling idea that the solar system is presently hosting an object whose journey has been shaped, at least in part, by purposeful use of the same gravitational architecture that human engineers have only recently learned to exploit. As the object continues its outward leg and approaches the region of space controlled most strongly by Jupiter, this geometric advantage becomes more than an academic note. It sets the stage for a specific test, a moment when the difference between a random interstellar path and a guided one could become visible in a small but decisive deviation near the giant planet's sphere of influence. As orbital analysts refine the path of 3I Atlas observers focused on its physical nature assemble a different kind of profile, one built from light curves, spectra, and the subtle modulation of brightness over time. Long before the hydrogen plume was reported, photometric monitoring hinted that the object is not tumbling chaotically. The pattern of its brightness variations when folded over different trial periods resolves into a relatively stable rotation, one that appears to maintain a consistent orientation with respect to the sun over large stretches of its inbound journey. This is not the norm for small bodies. Many comets and asteroids spin in complex ways, their axes precessing and nodding under the influence of uneven outgassing and past impacts. Their poles trace slow cones in space, and their surfaces alternately bake and freeze in irregular cycles. In contrast, 3I Atlas shows indications that its rotation axis points in a direction that remains broadly aligned with the sun as it approaches, as though the same hemisphere keeps facing the central star more often than random geometry would suggest. This behavior resembles in simplified form the spin stabilization used for some artificial satellites, where a constant rotation about a fixed axis helps maintain orientation and spreads thermal loads evenly. For a natural body, achieving and preserving such alignment over long timescales is difficult. Collisions and jets tend to randomize spin, not refine it. Yet, the light curves for 3I Atlas resist easy classification as fully random, leaving open the possibility that its rotational state has been shaped by more than uncoordinated forces. Alongside this dynamical portrait, spectroscopic teams working with large ground-based telescopes and space observatories focus on the composition of the material escaping from the object. By dispersing its light into a spectrum, they can identify the fingerprints of different elements and molecules present in the gas and dust. In the case of 3I Atlas, repeated observations converge on an unusual trait. The ratio of nickel to iron inferred from the spectra appears elevated compared to typical cometary compositions. On Earth and in many studied asteroids, iron and nickel tend to appear in proportions set by broad processes in planetary formation and differentiation. Deviations exist, but they usually fall within ranges that are now familiar. 3I Atlas seems to sit near the upper end of these ranges with nickel-rich signatures that require explanation. Nickel in itself is not exotic. It is a common transition metal found in planetary cores and meteorites. What draws attention is not its presence, but its relative abundance and the context in which it appears. In modern aerospace engineering, nickel-based alloys play a central role. They form the basis of materials used in turbine blades, rocket engine components, and structures that must withstand extreme heat and mechanical stress. These so-called superalloys retain strength at temperatures where ordinary metals would soften or fail. They allow engines to operate closer to their theoretical limits by reducing the risk of melting or creep. When scientists studying 3I Atlas note that its outgassed material appears unusually rich in nickel, they cannot help but register the parallel. They are careful to state that a high nickel content in a comet does not automatically indicate an engineered object. Natural processes in other star systems could produce bodies with metallic compositions, different from those found in the solar neighborhood. Yet, the combination of a potential fuel source in the form of abundant water and a surface or near-surface environment enriched in a metal commonly associated with high-temperature machinery raises the question of whether the object's physical makeup might be well suited to housing or integrating hardware that must survive repeated close passes by stars. The story becomes more nuanced when imaging of the coma and tail is examined in detail. High-resolution observations, though still unable to resolve the solid nucleus itself, can trace the structure of gas and dust jets that emerge from it. In many comets, these jets appear uneven and erratic, flaring from weak spots in the crust where sunlight and internal pressure open vents. The result is a fractured pattern of outflow shifting as different regions rotate into and out of illumination. 3I Atlas, by contrast, displays a coma whose larger-scale structure is surprisingly symmetric. Jet-like features in the gas appear to be arranged in a pattern that mirrors across axes through the nucleus, forming a balanced envelope rather than a chaotic spray. The overall tail maintains a dignity and steadiness that seems at odds with the notion of a fragmentary ice block shedding material in an uncoordinated way. Again, natural explanations exist, A body with a relatively regular shape, a smooth distribution of active regions, and a rotation state that presents similar surface areas to the Sun over time could generate a symmetric coma without any underlying design. Symmetry in outgassing does not require conscious arrangement of vents. It can arise from simple physics imposed on a consistent surface. Yet the combination of features now associated with 3I Atlas presses the boundary of what observers are willing to dismiss as coincidence. Here is an object that moves on a low inclination path through the planetary plane, carries a vast reservoir of water, emits a robust hydrogen plume whose evolution is not perfectly matched by standard sublimation models, rotates in a way that appears relatively stable and aligned with the star. It is passing exhibits spectral signatures pointing to nickel-rich material and sustains a coma whose jet structure looks notably ordered. Taken individually, each of these traits can be folded back into the category of quirks. Taken together, they build a profile that in another context might be recognized as deliberately tuned properties. If a civilization wished to design a long-lived interstellar carrier built around a natural nucleus, it might reasonably prefer a host with a composition that supports both structural integrity and high temperature tolerance, perhaps enhanced by nickel-rich alloys in reinforcing regions. It might seek to impose or maintain a rotation state that keeps critical surfaces within predictable thermal cycles and reduces tumbling that could complicate navigation or deployment of subordinate devices. It might select or adjust a set of exhaust outlets whose combined activity produces a symmetric, balanced torque profile, limiting unwanted changes in spin while still allowing for thrust when needed. The fact that 3I Atlas appears to meet some of these criteria does not prove that any such design has occurred. It does, however, make the object an excellent test case for exploring how far purely physical models can go in describing complex behavior before resorting to more speculative layers. Researchers comb through alternative natural scenarios. They consider the possibility that 3I Atlas is a fragment of a differentiated world whose metallic core material was partially exposed, or that it formed in a region of its birth system unusually rich in nickel-bearing minerals. They explore whether rotational alignment could arise through long-term torques exerted by asymmetric outgassing in its home system, slowly bringing its spin axis into a configuration that happens by chance to echo artificial spin stabilization. They simulate outgassing from a range of surface patterns to see how easily symmetric comas can form. In each case, some degree of conformity can be achieved between models and observations, but uncertainties remain. Small changes in input parameters can shift outcomes, and the true internal structure of 3I Atlas is unknown. No spacecraft has visited it directly. All inferences depend on photons collected at a distance and on the instruments that weigh and sort those photons into data products. Amid these careful efforts, the speculative narrative persists at the margins. In that narrative, 3I Atlas is not a pristine natural fragment, but a body that has been modified at least partially by technological activity. Nickel-rich regions might be manufactured shells or cladding around compartments that house power systems or computational units. The rotation axis might be actively maintained by occasional corrective jets. The symmetric coma might reflect thruster placement chosen to satisfy both cooling and maneuvering needs. In such a picture, the object's present appearance is the visible surface of a much deeper architecture, one that has merged engineered components with natural ice and rock so completely that from afar it remains indistinguishable from a comet in all but the fine details of its behavior. The scientific community as a whole does not adopt this view. It remains a hypothesis entertained in thought experiments and in a small number of unofficial discussions. Yet the very fact that serious experts feel compelled to outline how such a configuration would function shows how unusual 3I Atlas has become as a case study. It is an intersection point between planetary science, astrophysics, and long-range speculation about what interstellar technology might look like if it prefers camouflage over spectacle. With each new spectrum and imaging sequence, the object forces observers to refine both their natural models and their criteria for recognizing departures from them. In the process, it turns abstract questions about engineered comets and metal-rich carrier vessels into concrete, testable questions about one specific body visible in today's sky. 3I Atlas ceases to be an anonymous interstellar rock. It becomes a laboratory for thinking about how material motion and symmetry might encode intent, and about how close natural processes can come to imitating the outward signatures of design when no deliberate hand is present. As the physical and dynamical portrait of 3I Atlas grows more intricate, a different perspective begins to press in from the edges of the discussion, one that does not start with ice chemistry or orbital statistics, but with strategy. If an advanced technological system were moving through the galaxy and wished to avoid interference, the most straightforward way to do so would be to blend into the background. In the context of planetary systems, that background is not composed of sleek metallic holes and bright beacons, but of rocks, comets, and dust. Against the glare of a star, the easiest object to overlook is the one that resembles what astronomers expect to see, 3I Atlas, with its icy coma dust-laden tail and hydrogen plume, fits the profile of a comet so well that for many months it is treated as exactly that. Its discovery is logged, its orbit is fit, and its photometric behavior is catalogued. Only when the peculiar alignment, the hydrogen plume, the persistent outgassing, the symmetric jets, and the unusual metallic signature are all considered together does the possibility arise that this familiar appearance might itself be a form of concealment rather than a neutral fact. In human history, one recurring pattern in conflict and exploration has been the use of disguise to cross dangerous or unknown regions. A vessel that travels openly, projecting its nature and origin, invites interaction. That interaction can be peaceful, curious, exploitative, or hostile, but it is interaction nonetheless. A vessel that looks ordinary, carrying no obvious markers of value, often passes unhindered. Translated into interstellar terms, a reflective metallic craft broadcasting complex signals across many wavelengths would be conspicuous. It would draw attention from any technologically capable civilization in its path. That attention might come in the form of attempts to communicate, to intercept, or even to dismantle and study the object. By contrast, a body that looks like a generic comet would likely be logged as one more entry in a catalog of icy fragments. It would be surveyed briefly and then allowed to continue on its way. In the sample of alien searching strategies that can be imagined, most emerging civilizations direct their first efforts toward obvious signs of technology, such as artificial radio transmissions, laser flashes, or large-scale waste heat from energy collectors. Few focus on detailed behavioral anomalies in minor bodies, in part because the volume of rocks and comets is enormous, and in part because resources for close scrutiny are finite. This asymmetry in attention creates a narrow channel in which a hidden craft can move. By embedding hardware within or beneath a natural comet-like shell, a civilization gained several advantages at once. The surrounding ice and dust provide physical protection against micrometeoroids and high-energy particles, extending the lifetime of sensitive components by orders of magnitude. The mass of the host body also serves as a radiation shield, smoothing out the flux of cosmic rays and solar storms over deep time. At the same time, the volatile content of the host doubles as fuel. Water and other ices can be processed into propellant, allowing the composite object to maneuver without revealing any obvious engines on its surface. In this configuration, the visible cometary activity is not merely tolerated, but deliberately maintained. Gas jets and dust streams serve a dual purpose. They radiate away heat generated by internal systems helping regulate temperature, and they maintain the illusion that all observed activity is the result of sunlight on ice. To an external observer, the body appears to be behaving exactly as a natural comet should, even if the timing and distribution of its outgassing are subtly tuned from within. 3. Atlas, seen through this speculative lens, becomes a textbook example of such a Trojan strategy. Its surface, as far as can be resolved, looks typical. Its brightness evolution follows a general pattern expected from an icy visitor, and its tail points broadly away from the sun. Yet beneath this familiar exterior, there could in principle be a network of cavities, conduits, and compartments enclosing machines that convert stored chemical or nuclear energy into electrical power, run electrolysis units to split water, and feed hydrogen to thrusters embedded near the surface. The nickel-rich material hinted at in the spectra could form structural ribs and casings around these systems, protecting them from the stresses of repeated stellar flybys. Over millions or even billions of years, such an arrangement could drift from star to star, waking briefly whenever a new system's light falls across it, performing observations, perhaps releasing small probes, adjusting course, and then returning to dormancy as it moves back into the dark. Even without accepting this narrative as true, it is instructive to examine how it intersects with the human response to 3I Atlas. Within the scientific community, there exists a strong bias toward natural explanations. This bias is not a flaw, but a necessary safeguard. History shows many examples where seemingly anomalous phenomena yielded to more careful measurements and improved models without the need to invoke extraordinary mechanisms. As a result, any suggestion that an observed object might embody alien technology is met first with skepticism, often strong skepticism. Researchers look for instrumental artifacts, modeling errors, or overlooked physical processes before entertaining more exotic ideas. This caution acts as an additional layer of camouflage for any real technological object that might exist. Even if subtle signs of control or engineering are present in data, the default response is to ask whether they can be reconciled with known physics, driven solely by natural conditions. Only when such efforts fail comprehensively and when the anomalies persist across instruments and teams does the balance of plausibility begin to shift. 3I Atlas sits in an intermediate zone. Its behavior is unusual enough to stimulate speculative frameworks, but not so clearly beyond natural models that those frameworks become dominant. The hydrogen plume can still be fitted with complex sublimation scenarios. The metallic composition can still be ascribed to formation in an unfamiliar environment. The low inclination trajectory can still be treated as a statistical outlier. Each anomaly, when isolated, can be incorporated into an expanded picture of what interstellar debris might look like. The result is that any hypothetical concealment strategy used by an advanced system does not need to be perfect. It does not need to erase every sign of internal activity. It only needs to ensure that the remaining signs are plausibly attributable to nature. The burden of proof then shifts to those who would argue for a technological interpretation, and that burden is high. This dynamic is mirrored in the public conversation that surrounds 3I Atlas. Enthusiastic observers outside the formal research community quickly adopt terms like alien probe and artificial comet, while many professionals push back, reminding audiences that extraordinary conclusions based on limited data are premature. The contrast between these reactions creates an environment in which the most conservative view has institutional support, while more radical possibilities are confined to speculative commentary. In a sense, this social structure itself becomes part of the potential camouflage. A real technological object could pass through a system confident that most of its hosts' authoritative voices would resist labeling it as such, even in the face of suggestive evidence. As the Solar and Heliospheric Observatory, the James Webb Space Telescope, and other instruments continue to monitor 3I Atlas, they inadvertently participate in this layered game. Teams search earnestly for signatures of internal heat sources such as excess infrared radiation on the night side of the object that cannot be explained by sunlight re-radiating from warmed surfaces. They watch for non-gravitational maneuvers that cannot be matched to observed gas emission. They look for transient flashes or narrow beam emissions that might indicate active communication or sensing. At the same time, they calibrate their tools against known comets, refine their understanding of natural variability, and expand the range of what is considered normal behavior for icy interstellar visitors. Every detection that stretches the natural models without clearly breaking them adds to a growing catalog of borderline cases. 3I Atlas stands at the forefront of this catalog. It is both a target of observation and a mirror in which the assumptions of the observers are reflected back. It demonstrates how much complexity can be generated by unplanned physical processes alone, and how easily from a distance that complexity can imitate what might be expected from deliberate design. It also demonstrates how a plausible concealment strategy would look if one were in operation. In a galaxy where the number of comets and comet-like bodies is beyond counting, a single engineered carrier hidden among them would be statistically almost invisible. Its recognition would depend on a rare alignment of factors, sufficient instrumental sensitivity, a suitable trajectory that brings it near planets with observatories, and a scientific culture willing to articulate and test hypotheses that sit at the edge of current understanding. For now, 3I Atlas remains an ambiguous case. It behaves too oddly to be ignored and too plausibly like a comet to be confidently classified as anything else. The very tension between these views is what makes it compelling. As it moves outward toward the domain dominated by Jupiter, the question of camouflage shifts from a static description to a dynamic one. If the object is disguised, does that disguise persist unchanged, or might it slip during moments of high stress, such as a close planetary encounter, where internal systems must work harder to navigate competing gravitational pulls? The next phase of its journey, therefore, is not only a test of orbital mechanics, but also a test of how robust any hypothetical concealment might be when the demands of steering and resource management increase. With the outer behavior of 3I Atlas cataloged in growing detail, attention turns inward toward a volume that no telescope can yet resolve, and that remains in a literal sense dark. The visible coma, the hydrogen plume, the symmetric jets, and the nickel-rich spectral hints all emerge from a thin shell near the surface. Beneath that layer lies the bulk of the object, a mixture of ice rock and possibly metal, whose exact arrangement is unknown. In the standard comet picture, this interior is a porous aggregate, a loosely bound matrix of frozen volatiles and dust riddled with voids. In the speculative picture that now shadows the standard one, that interior becomes something more structured, a host medium threaded with conduits, cavities, and compartments that support machinery. The two pictures are not mutually exclusive. In fact, any technologically altered 3I Atlas would almost certainly begin as a natural body, whose existing porosity and layering are exploited rather than erased. The first requirement for any long-lived system buried within such a host is power. Over the timescales involved in interstellar travel, no chemical battery can suffice. The energies needed to perform even modest course corrections, drive electrolysis of water, and operate sensors and processing units demand sources that either regenerate or release stored energy slowly over millions of years. Human spacecraft rely on radioisotope thermoelectric generators or solar panels, but radioisotopes decay within finite intervals, and solar power streams from discrete stars. In the deep dark between systems far from any star, a truly long baseline vehicle would require something more persistent. Perhaps compact fission reactors, long-lived radioisotope assemblies with much greater mass than those currently flown from Earth, or power plants that tap into physics not yet mastered by human engineers. Any such source would generate heat, and in a closed environment, heat must be managed. 3I Atlas, as seen from the outside, is an efficient radiator. Its irregular surface and extended coma provide a vast area over which infrared energy can be emitted back into space. If internal reactors exist, they would have to couple their waste heat into this natural radiator without producing localized hotspots so intense that they betray their presence in current thermal data. Designs that spread heat through a network of conductive pathways and phase change materials become plausible here. Ice near the core could be melted and refrozen in cycles that absorb and release thermal energy, smoothing out peaks. Layers of nickel-rich alloys, if present, could distribute heat efficiently through a metallic lattice before it reaches the outer shell and is carried away by sublimating gas. In this view, the very act of venting water and gas into space is part of a controlled thermal management system as well as a means of generating thrust. From a scientific standpoint, the key observational consequence of such an interior would be a pattern of infrared emission that cannot be accounted for by sunlight alone. As 3I Atlas rotates, different facets of its surface move into and out of direct illumination. A purely passive body warms and cools, according to well-understood thermophysical principles governed by its albedo thermal inertia and surface roughness. The James Webb Space Telescope and other infrared-sensitive instruments can model these processes and predict how bright the object should be at various wavelengths as a function of time, day side, and night side. Any persistent excess on the night side or any modulation that correlates poorly with solar input might indicate an additional heat source within. To search for such deviations, teams build detailed thermophysical models of 3I Atlas, using the best available estimates of its size, spin state, and surface properties, then compare those models to measured fluxes. Early results do not show glaring discrepancies, but the limits are not yet tight enough to rule out moderate internal power. With the object at great distances and still partially shrouded by its own coma, small hot regions, a few tens of degrees warmer than their surroundings, could remain undetected. As sensitivity improves and as the object moves into geometries that favor clearer views of its night side, this line of inquiry becomes more critical. Alongside heat flow, the interior must also manage matter. If water ice is being harvested and split, then hydrogen must be transported from reservoirs to outlets that serve as thrusters. In the natural picture, gas flows through fractures as pressure gradients drive it toward the surface. In the engineered picture, those fractures might be supplemented or replaced by pipe-like conduits, channels deliberately widened or carved to guide flow. At junctions, valves and regulators could meter the rate at which hydrogen is allowed to escape. Compartment walls might separate regions devoted to different functions such as power generation, propellant processing, data storage, and external sensing. Over long durations, the line between natural void and artificial tunnel could blur as ice sublimates, walls deform, and structural supports freeze into the surrounding matrix. A deep radar sounding instrument aboard a nearby spacecraft could, in theory, distinguish between these scenarios by mapping the internal density distribution. In practice, no such probe has yet been dispatched to 3I Atlas, so the interior remains a domain inferred only by analogy and necessity. The necessity arises not only from propulsion, but also from control. To steer itself effectively, an interstellar carrier would need a system capable of interpreting sensory input, planning responses, and executing them in a coordinated way. That system, whether based on electronics, photonics, or some unfamiliar substrate, would require a protected environment free from rapid thermal swings and shielded from the most damaging radiation. The core of 3I Atlas, buried under tens or hundreds of meters of ice and rock, offers precisely such a sanctuary. In that sanctuary, an artificial intelligence could operate intermittently, entering low power states for long cruises, then waking fully when a star's light grows strong or when external detectors register something of interest. The logic of such a mind would include not only navigation and resource management, but also decisions about interaction. If the craft were designed to avoid contact, it might adjust its behavior to minimize signatures whenever it detects radio emissions or other signs of a technological civilization nearby. If its purpose includes observation, it might instead alter its trajectory to gain better vantage points on planets that show atmospheric anomalies or artificial emissions. From the standpoint of current observers on and around Earth, this hypothetical interior intelligence is both unreachable and testable. It is unreachable because no signal, no probe, and no physical sample can yet penetrate the ice shell to reveal the presence or absence of circuits. It is testable indirectly because any internal decisions that affect propulsion will inevitably alter the object's motion and outgassing in ways that can be measured. Excess hydrogen production, timed to coincide with optimal windows for gravity, assists non-gravitational accelerations that do not match the integrated pattern of observed jets or sudden shifts in coma structure that line up with external stimuli, could all hint at more than physics alone. In this sense, the interior is projected outward into the behavior of the envelope. Scientists comb through time series of images, spectra, and astrometric positions looking for correlations. They check whether spikes in hydrogen emission align with specific orbital phases, such as approach to the Sun or to Jupiter, whether subtle kinks in the path occur where no natural irregularity in outgassing is expected, and whether any transient flashes of light appear at unusual wavelengths that might denote active transmissions. To date, no single observation has crossed the threshold from suggestive to compelling. The hydrogen plume is strong, but can still be stretched to fit sublimation models with internal lag. The non-gravitational accelerations exist, but can still be matched to asymmetric venting and plausible thermal inertias. The infrared signal is informative, but not clean enough to reveal compact reactors. The absence of definitive anomalies does not close the case, however. It merely sets upper limits on how much power can be operating inside 3I Atlas without detection, and on how tightly any hypothetical internal processes must be coupled to natural ones. For a civilization of sufficient sophistication, these constraints might be trivial to meet. If embedded systems are small compared to the mass of the host, their waste heat may be negligible compared to solar input near perihelion. If their course corrections are modest and spread over long intervals, their contribution to non-gravitational accelerations could be indistinguishable from buildup of natural jets. If their communications use narrow beams aimed deliberately away from known sources of interference, the chance of an accidental intercept by instruments clustered around one small planet becomes small. In that light, the failure to see decisive evidence of engineering inside 3I Atlas is not surprising. It is precisely what a well-designed covert carrier would aim to achieve. At the same time, the object's existence and the detailed observations now being made transform the idea of such interiors from distant speculation into something that can be parameterized. Researchers can now say with quantitative backing how much hidden power is compatible with the measured infrared flux, how large a deviation in thrust would be allowed by current ephemeris uncertainties, and what kind of small probe release events would be detectable in the structure of the coma. This process effectively maps the observational boundary between natural and artificial for one specific interstellar body. Inside that boundary lies a wide space in which an interior of machines and conduits could conceivably operate undetected. Outside it, the more blatant configurations of a science fiction imagination are already excluded. 3I Atlas is therefore not only a subject, but also a calibration tool. It shows how thin the line can be between what is inferred and what remains hidden. As it travels onward, the unseen interior continues to exert a quiet pull on the narrative, shaping the questions investigators ask and the measurements they prioritize. The ice shell and hydrogen plume are what instruments see, but In the calculations, in the models, and in the speculative frameworks built around them, there is always the ghost of a space within a volume that could be emptiness, porous ice, or an intricate architecture of alien machines, all producing the same distant shimmer in a handful of telescopes pointed at a moving point of light. As models of the possible interior of 3i Atlas grow more elaborate, a deeper constraint begins to frame all of this speculation, a constraint imposed not by the object itself, but by the scale of the galaxy. Any device traveling between stars must contend with the finite speed at which information can move. The diameter of the Milky Way is on the order of tens of thousands of light years. Even a single traverse across its disk would take a light signal tens of thousands of years to complete. In that context, the familiar image of a mission control center steering a craft in real time from a home world becomes untenable. By the time an instruction leaves one side of the galaxy and reaches a vessel near the other, the conditions that motivated that instruction will have changed beyond recognition. Planets will have moved, stars will have drifted, and the craft itself will have long since passed any point where the command could meaningfully apply. Applied to 3i Atlas, this basic limit implies that if any technological system is indeed riding within or upon the object, it cannot be relying on live guidance from a distant civilization. Whatever decisions govern its path and behavior must be made locally by systems carried with it. In more familiar terms, 3i Atlas would not be a remotely piloted vehicle, but an autonomous probe. Even if a civilization wished to maintain some measure of strategic oversight, that oversight would take the form of initial programming and perhaps occasional updates delivered at very long intervals, not continuous control. Between those rare moments of synchronization, the craft would have to interpret its environment, assess its options, and act according to internal rules. Within this framework, the idea of an artificial intelligence at the core of 3i Atlas ceases to be an embellishment and becomes instead a nearly unavoidable conclusion if the engineered carrier hypothesis is entertained at all. A simple mechanical autopilot might suffice for a single crossing from one star to another along a predetermined route, but it would struggle to adapt to unforeseen circumstances. Over millions of years, the gravitational field of the galaxy changes potential refueling bodies, drift in and out of reach, and target systems move along their own orbits around the galactic center. An adaptive intelligence capable of learning from its encounters and updating its strategies would handle such variability far more effectively than a fixed set of instructions. This intelligence need not resemble human minds in any detail. Its priorities could be narrow and specific, focused on navigation, resource management, and observation without the broader range of emotions and drives associated with biological life. Yet, it would still possess the defining property of being able to choose among options available to it in real time within the constraints of its design. If such a system inhabits 3i Atlas, it now finds itself in a comparatively crowded environment after perhaps long epochs spent in near-perfect darkness. As the object has approached the sun, it has moved from the quiet of interstellar space into a region filled with electromagnetic noise from human activity. Radio transmissions, radar sweeps, satellite links, and the thermal signatures of industrialized planets all contribute to a background quite unlike the one it would encounter near a star without technological life. Sensitive receivers embedded in the interior could detect this shift well before human instruments registered anything unusual about the object itself. In that scenario, the artificial mind, if present, would have advance warning that it is entering a system where at least one world harbors machines. The strategies it might adopt in response depend on its mission profile, which is unknown. A probe designed solely to collect data might adjust its path to secure better vantage points on the source of the signals, perhaps aiming for an orbit that allows repeated views of Earth and other planets. A probe designed to avoid interference might instead minimize its interaction with the inner system, maintaining a path that satisfies some observational goals while reducing the chance of interception. Uncertainty about intent not only limits what observers can infer, but also shapes which behaviors they look for. In practical terms, astronomers have begun to monitor 3i Atlas for signs of responsiveness changes in its activity pattern that correlate not only with orbital phase but also with external events. One can imagine, for example, transmitting directed radio beams or laser pulses toward the object and watching for any alteration in outgassing or trajectory that follows. Such experiments remain controversial, in part because any active attempt to interact with a possible technological artifact raises policy questions that go beyond astrophysics, and in part because the chances of a clear response are considered low. For now, most monitoring remains passive. Instruments record the natural variations in gas production, rotation, and motion, and analysts search for patterns that cannot be easily tied back to sunlight gravity or internal lag. Within this passive approach, the notion of an artificial pilot manifests in subtle ways. If a mind is guiding 3i Atlas, its influence would show up where natural drivers fail to account for the observed sequence of events. Consider the hydrogen plume. In a purely physical picture, its evolution is dictated by distance from the sun, thermal conduction, and structural changes within the ice. In the presence of an internal decision-maker, the timing of hydrogen release could also encode a strategy, such as conserving resources until the object reaches a point where a small thrust has an outsized effect on its orbit. A comparable logic applies to gravity assists. Human mission planners choose the timing and orientation of planetary flybys with care, knowing that slight adjustments before a close approach can drastically alter a trajectory afterward. An artificial intelligence with a detailed model of celestial mechanics could do the same, adjusting outgassing to fine-tune the path of its host. When observers look ahead to the forthcoming passage of 3i Atlas near Jupiter's sphere of influence, they see not only a natural test of non-gravitational acceleration models, but also, potentially, a planned maneuver window for any internal system. Jupiter's Hill sphere, the region within which its gravity dominates over that of the Sun, extends far into space. A body entering this region can be deflected, captured, or slung outward depending on its velocity and approach direction. If 3i Atlas is guided, this encounter would be a prime opportunity to redirect its outbound course toward a chosen sector of interstellar space, perhaps aiming at a specific subsequent target star, or at a region rich in interstellar material. In that case, one might expect to see a pattern of gas release or a small thrust near closest approach that does not line up neatly with temperature-driven outgassing alone. Calculations already underway attempt to predict what such a maneuver would look like in the data. Analysts generate families of trajectories that differ by tiny changes in velocity, applied near the Jupiter flyby, then propagate them forward to see how they diverge from the purely gravitational path. They establish thresholds beyond which deviations would be statistically significant given the precision of current and planned observations. They also ask how much mass loss would be required to produce such deviations and whether that mass loss is compatible with the observed hydrogen plume. The results indicate that even modest directed thrusts applied at the right moment near Jupiter could lead to measurable shifts in the object's outbound track shifts that would be difficult to reproduce with random jets alone. In effect, the coming encounter becomes an experiment in detecting agency. If nothing unusual happens, and if the trajectory follows the gravity-dominated prediction within uncertainties, the case for a natural object strengthens. If a discrete, well-timed deviation is observed, especially one accompanied by no corresponding spike in visible outgassing or one that appears coordinated with the geometry of the encounter, the argument for an internal pilot gains weight. Yet even here, caution is warranted. Jupiter's complex gravitational environment, combined with incomplete knowledge of 3I Atlas's internal structure and rotation, can produce subtle effects that may masquerade as directed maneuvers. A rigorous analysis would be required to separate chance from intention. Beyond specific tests, the broader presence of an artificial intelligence has implications for how 3I Atlas is perceived not as a passive target, but as a participant. If the object is capable of registering that it is being watched, its behavior might be contingent on that awareness. It could, for example, modify its activity to appear more natural when it detects concentrated observation, or it might use human instruments as beacons to refine its own understanding of the system's layout. In a more speculative mode, one can imagine it choosing to reveal itself through a controlled anomaly only once certain criteria are met, such as confirmation that the local civilization has reached a particular level of technological maturity. For now, such scenarios remain conjectural. Nonetheless, they influence the design of observational campaigns. Teams consider whether to cluster their monitoring near key dates or to spread it out, whether to focus on a few wavelengths or to cover a broad range, and whether any attempt should be made to send deliberate signals. In every case, they balance scientific curiosity against prudence, aware that 3I Atlas, if inhabited by an artificial mind, might interpret attention in ways that cannot be predicted. All of this takes place against the backdrop of a galaxy that is on human timescales almost unimaginably slow. Stars complete their orbits around the galactic center over hundreds of millions of years. Civilizations, if they arise, may flare and fade in much shorter intervals. An interstellar probe, like the speculative 3I Atlas carrier, must therefore be robust not only in hardware, but also in purpose. Its artificial pilot would need to carry on even if its makers vanish, continuing to traverse the disk cataloging worlds and perhaps seeding information for successors yet unborn. In that sense, the object would be a form of persistent memory for a species, a stored intention, moving through space long after any direct connection to its origin has been lost. Observers on Earth, looking up at the point of light that marks its passage, find themselves entangled in this possibility. They do not know whether 3I Atlas is guided or inert, but they cannot fully exclude the idea that somewhere beneath its surface, logic circuits or their equivalent are ticking through decision trees evaluating gravitational potentials, counting photons, and adjusting hydrogen flows in response. The hydrogen plume, the orbital alignment, the rotation axis, and the metallic composition become not just physical facts, but potential expressions of an underlying algorithm playing out over astronomical distances. Even if 3I Atlas is entirely natural, the exercise of contemplating an autonomous artificial pilot within it proves valuable. It forces a clearer articulation of what kinds of behaviors would constitute evidence of agency versus evidence of complex physics alone. It sharpens the tools with which future interstellar visitors will be examined, and it introduces an awareness that the next object of this kind may not be so ambiguous that one day a body may arrive whose pattern of motion, heat, and emission cannot be plausibly ascribed to chance. 3. I-Atlas thus occupies a threshold position. It is a bridge between a sky once thought to contain only stars and planets, and a sky that may in truth also contain long-lived machines. As it moves toward its encounter with Jupiter, the question of whether it is steered by an artificial mind remains open, but the very act of asking that question marks a shift in how humanity reads the small moving lights that cross the solar system from beyond. As 3I Atlas moves outward along its post, perihelion leg calculations converge on a date that has been circled quietly in mission planning documents and observatory schedules. In mid-March of the year 2026, the object will pass near the boundary of Jupiter's gravitational domain, entering and then exiting the region known as the Hill Sphere, where the pull of the giant planet temporarily outweighs that of the Sun. This is not a close flyby in the sense of a spacecraft skimming cloud tops, but on astronomical scales, it is intimate, a passage through an invisible volume of influence that has shaped the orbits of countless smaller bodies over the history of the solar system. For any object on a hyperbolic trajectory, such an encounter presents a fork in its path. Gravity alone can bend its course, altering the direction and speed with which it leaves the system. If, in addition, there is any ability to apply thrust at key moments, the encounter becomes an opportunity to sculpt a trajectory with remarkable precision. Human mission designers have long exploited this leverage. Probes sent to the outer planets and beyond have used Jupiter's mass as a slingshot, gaining energy or redirecting their paths with minimal fuel expenditure. The equations describing such gravity assists are well understood. Given an incoming velocity and approach, Angle 1 can calculate a family of possible outgoing trajectories depending on where, relative to the planet's motion, a small additional thrust is applied. A burn performed just before or just after closest approach can tip the balance between a path that climbs above the planetary plane, one that dives below it, or one that remains within it, but shifts to a new orientation around the Sun. Applied to 3I Atlas, this framework turns the upcoming encounter into a natural experiment. If the object is entirely passive, its path through Jupiter's Hill Sphere will be dictated by gravitational forces alone and by whatever non-gravitational acceleration arises from outgassing that continues in broadly predictable ways. Modest deviations from purely gravitational predictions are expected under this natural picture and can be modeled. If, however, an internal system is timing hydrogen release to act as thrust in concert with the planetary flyby, the resulting trajectory could differ in characteristic ways. Even a small, well-directed push can produce an outbound path that diverges measurably from the one set by gravity and random jets. To prepare for this test, teams around the world refine the pre-encounter ephemeris of 3I Atlas with great care. Every new astrometric measurement, every updated position from space-based and ground-based observatories is fed into orbit determination software to reduce uncertainties in its predicted location at the moment it approaches Jupiter's sphere of influence. The aim is to narrow the cone of possible paths so tightly that any subsequent deviation beyond modeled ranges must be explained by processes beyond ordinary outgassing. Parallel efforts simulate a wide range of non-gravitational scenarios, from isotropic sublimation that produces minimal net thrust to strongly asymmetric jets that push persistently in fixed directions tied to the object's rotation. These simulations establish a baseline of how far the actual trajectory could plausibly wander, even if all activity is natural. Against this baseline, the predicted signatures of a deliberate maneuver are plotted. A carefully timed thrust near closest approach, aligned in a direction that maximizes or minimizes the energy exchange with Jupiter, can shift the asymptotic outbound velocity and direction by small but measurable amounts. The threshold for detection depends on the precision of post-encounter tracking, but analysts know roughly what to look for: an ephemeris that diverges systematically from the gravity plus natural outgassing model, not in random oscillations, but in a coherent offset that grows steadily over time. While celestial mechanicians focus on paths, other teams consider how the internal state of 3I Atlas, if artificial, might shape its maneuver strategy. A system intent on conserving resources might choose the minimal thrust that still accomplishes a significant redirection, using the immense mass of Jupiter as the primary agent of change and its own hydrogen only as a fine-tuning tool. In that case, the mass of water expelled as reaction mass during the maneuver would not need to be large compared to what has already been observed. The previously measured 13.5 million metric tons of water and whatever additional loss occurs between now and the encounter provide ample potential propellant for such a modest burn. The crucial factor would then be the timing and orientation of gas release rather than its volume. Natural sublimation is governed largely by the pattern of sunlight over the rotating surface. A guided thrust, by contrast, would be aligned with a desired change in velocity, even if that alignment is achieved by adjusting which vents are active when and by how much. Instruments capable of mapping the structure of the coma around the time of the flyby could, in principle, detect such selective activity if the jets show patterns that do not match the simple illumination geometry. Observers therefore plan coordinated campaigns, scheduling telescopes to watch 3I Atlas before, during, and after the Jupiter encounter. Optical and ultraviolet instruments will trace the evolution of the hydrogen plume and the dust coma, while infrared sensors will monitor for any changes in thermal emission that might accompany an internally powered maneuver. Radio telescopes may also be brought to bear, listening for transient signals that could coincide with a period of heightened internal activity. The goal is to build a multi-wavelength record that can be compared against both natural and speculative models. At the same time, there is an awareness that the most telling signature may be the simplest the path itself. For all the complexity of gas flows and spectral lines, the motion of a mass in a gravitational field obeys strict rules. Any sustained deviation from those rules, when all known forces are accounted for, implies either missing physics or missing agents. The Jupiter encounter is uniquely suited to this kind of test because gravitational influences there are strong enough and structured enough that the shape of the trajectory is especially sensitive to small pushes. To appreciate this one, can imagine 3i Atlas as a stone skipping through a moving stream. The position at which it enters the current and the orientation of its motion at that instant determine how it will be carried downstream. A small shove at the moment of entry can alter the line of travel far more than an equivalent shove applied in still water later on. In March of 2026, the interstellar object will pass through just such a current, the dynamic field of a giant planet in motion around the Sun. Whether it simply drifts with that field or tries to ride it in a particular way is the core question. Adding further depth to this test is the way it interfaces with the broader context of interstellar navigation. A probe that uses ice-rich bodies as carriers and refueling stops would likely evolve strategies that exploit major planets systematically. In other words, if 3i Atlas is one of many such vehicles, its encounter with Jupiter would not be an isolated experiment, but part of a long-established method. Human engineers already know that the most efficient routes through planetary systems often chain together multiple gravity assists. An artificial intelligence designed for interstellar travel would almost certainly have discovered the same principles, perhaps long ago. Thus, watching for sophisticated use of the Jupiter flyby is not only a test of whether 3i Atlas is guided now, but also a test of whether any guiding system has adopted optimization strategies similar to those found independently on Earth. If the object's outbound trajectory once measured matches almost exactly the path that human mission planners would choose for a craft trying to reach certain classes of target orbits, the parallel would be difficult to ignore. On the other hand, a natural object obeying only gravity and irregular outgassing might well leave the encounter on a path that, while influenced by Jupiter, falls somewhere in the broader space of possible outcomes without any clear optimization. The period between the current moment and the March encounter therefore becomes a time of preparation. Observatory time is requested, simulations are refined, and data pipelines are tested to ensure that any subtle change in measured position or brightness near the encounter is not lost in noise. 3. Atlas itself, indifferent in appearance, continues along its path, its hydrogen plume expanding its jets, flickering in patterns that may or may not encode intention. From the vantage point of Earth, the event represents a kind of cosmic examination. The object will be placed in a context that amplifies the consequences of any internal decisions it might make. If the internal architecture is inert, the result will be one more data point in the growing catalog of interstellar bodies, valuable for refining models of comet physics and orbital dynamics. If, in contrast, there is an active system within the Jupiter flyby, is the moment when that system's hand, however subtle, is most likely to leave a detectable fingerprint on the sky. In either case, the encounter has already changed how scientists think about 3i Atlas. It shifts the narrative from a static catalog of properties to a dynamic story in which the object's future motion can confirm or challenge the frameworks built around its past. It forces a deeper integration between observational astronomy, which tracks the light and motion of bodies, and speculative astrodynamics, which imagines how a distant intelligence might choose to move through complex gravitational landscapes. As the calendar inches toward mid-March 3, iAtlas becomes not just an object of study, but a participant in a scheduled test, a traveler whose turn through the largest planet's sphere of influence will either reinforce the view of a natural comet rich in quirks or open a small but significant crack through which the presence of guidance, however ancient and remote, might be inferred. As the date of the Jupiter encounter approaches and then passes into the near future, the picture of 3I Atlas that has formed over months of observation settles into a curious balance between what is known and what remains open. On the side of established fact stands a set of measurements that, taken together, already make this object one of the most informative interstellar visitors yet recorded. Instruments have revealed a massive hydrogen plume appearing days after perihelion and persisting over weeks, implying the loss of roughly 13.5 million metric tons of water in a short span of time. Orbital fits have shown that the object moves on a hyperbolic trajectory, with a small inclination relative to the planetary plane, a path unusually well suited to encounters with multiple worlds, and with Jupiter's extended sphere of influence. Photometry and spectroscopy have hinted at a rotation state that maintains a stable orientation toward the Sun, and at outgassing patterns that produce a symmetric coma. Spectral lines have suggested an elevated nickel-to-iron ratio, when compared with common solar system comets, raising questions about the internal makeup of the nucleus. None of these findings depends on speculation. They are the scaffolding on which models are built. On top of this scaffolding, however, stands an increasingly detailed structure of interpretation, and it is here that 3I Atlas begins to play a different role. Regardless of whether the object carries any technology, it has become a reference point for thinking about what an interstellar machine might look like if it exploited natural bodies, rather than relying on standalone ships. The hitchhiking hypothesis, which treated ice-rich objects as potential carriers and fuel tanks for automated systems, now has a concrete example against which to test its assumptions. The hydrogen plume demonstrates that water of the necessary scale is present. The low inclination orbit demonstrates that a trajectory can be arranged, whether by chance or design, that passes close to planetary planes and gravity wells. The rotational behavior and symmetric jets demonstrate that outgassing can, under some circumstances, produce patterns reminiscent of controlled thrust without immediately breaking natural models. In this way, 3I Atlas becomes both an object of interest in itself and a template for future searches. Observers now know which kinds of signatures to look for when the next interstellar body is detected. An unusually vigorous hydrogen cloud, especially one whose evolution deviates from simple distance-based expectations, will draw closer scrutiny. A trajectory that aligns strongly with a new system's planetary plane will be recognized not only as a geometric curiosity, but also as a potential indicator of optimized passage. Comae with sustained symmetry rotation axes that maintain stable orientations toward host stars and metallic compositions at odds with standard formation environments will all stand out more sharply against the background of ordinary comet behavior. 3. iAtlas has, in effect, expanded the parameter space of what is considered worth flagging for detailed study. At the same time, the object has practical implications for how humanity might someday attempt to cross interstellar distances. The traditional model of a large self-contained starship, powered by massive fuel reserves, lifted from a home world runs directly into the limitations of chemical propulsion and the cost of pushing huge masses out of a deep gravitational well. 3I Atlas and objects like it suggest an alternate mode of travel. Instead of building an entire interstellar craft from scratch, a civilization could send comparatively small payloads to rendezvous with passing interstellar objects already moving at high velocities. These payloads could carry drilling equipment, power sources, and control systems designed to burrow into the ice and rock, establishing themselves within the host. Once installed, they could gradually convert local resources into fuel for modest course corrections. Over time, such hitchhiking probes could guide their carriers toward target stars without the need to accelerate from rest across the entire distance. The first step in this strategy would be local identifying suitable candidates as they pass through the home system and delivering payloads to them. 3I Atlas shows that such candidates exist and that they can be identified with current surveys. The second step would be technological developing automated systems capable of operating for timescales far beyond human lifetimes and enduring the harsh conditions inside an ice and rock matrix. The third step would be conceptual, accepting that interstellar missions might be measured not in decades or centuries, but in thousands or millions of years, with probes that act as patient archivists of a civilization rather than as crude vessels. In this context, the possibility that 3I Atlas already carries such an embedded system placed there by another species long ago becomes more than an intriguing idea. It becomes a potential glimpse at methods that have already been tested elsewhere. If that is the case, then humanity is not only observing a visitor, but also receiving a demonstration of a technique that could be imitated, adapted, or extended. The underlying physics of water electrolysis, hydrogen propulsion, and gravity assists are universal. Any civilization that discovers them can use them. A carrier that uses natural comets and asteroids as shells would be, in this sense, a practical lesson in interstellar engineering moving through the solar system. Yet, there is an additional, more subtle implication. If 3I Atlas is natural in every respect, then the fact that it so neatly fits the requirements of the hitchhiking model highlights how closely technology can align itself with existing structures. The same properties that make an object a good candidate for hosting machines are also produced by purely physical processes in distant systems. Water accumulates in outer regions of protoplanetary disks. Nickel and iron concentrate in certain types of planetesimals. Gravitational interactions can eject bodies onto hyperbolic paths aligned with galactic motion. In such a universe, the distinction between a potential vehicle and an inert rock is not structural, but functional. A comet becomes an interstellar craft when something chooses to use it as such. 3I Atlas underlines this equivalence. It shows that the galaxy naturally assembles objects that could serve as vehicles if someone were to inhabit them. The line between environment and infrastructure is thin. This realization shapes more than future engineering plans. It also informs the search for signs of extraterrestrial activity. Traditional strategies often focus on detecting signals broadcast deliberately across space or on finding large-scale artifacts such as vast energy collectors. 3I Atlas suggests that another class of evidence may lie in the detailed behavior of small bodies. A technological imprint might be subtle, encoded in slight deviations from expected thermal emission in carefully timed outgassing events, or in paths that take full advantage of planetary alignments. To extract such evidence, long baseline monitoring of interstellar visitors is required along with models of natural variability robust enough to flag genuine anomalies. The current observations represent early steps in this direction. In addition, the object introduces the unsettling possibility of shared infrastructure. If a civilization chooses to use interstellar comets as carriers, there is nothing to prevent another civilization from doing the same with the very same bodies at different times. Over the lifetime of a galaxy, an object like 3I Atlas could host more than one technological occupant, each leaving layers of modification, each perhaps unaware of the others. In a distant future scenario, a probe launched from Earth might eventually rendezvous with a comet only to find pre-existing hardware buried in the ice dormant or active from a species that passed this way in a previous epoch. The common carrier would then become a meeting point, not in time, but in place, a shared tool used by beings separated by millions of years. 3I Atlas makes such images more concrete. It shows that the carriers exist and that they can endure the stresses of interstellar flight. The rest is a question of who chooses to use them. Throughout all of this, one fact remains unchanged. From the standpoint of current knowledge, there is no conclusive proof that 3I Atlas is anything other than a complex natural object. Every anomaly in its behavior can still be stretched to fit within the boundaries of known physics applied to unfamiliar initial conditions. At the same time, the hypothesis that it may host or once have hosted an artificial system is not in open contradiction with any measurement either. It remains a viable, if speculative, narrative layered over the data. The balance between these views is likely to persist. As the object recedes into the outer darkness, tracking it will become harder, and detailed monitoring of its activity will give way to coarser positional updates. The window in which high-resolution evidence could be gathered is limited. Once it closes, many of the central questions will remain unresolved. Did the hydrogen plume arise solely from internal thermal lag, or did it include episodes of directed thrust timed to orbital milestones? Is the elevated nickel content a sign of unusual formation processes or of structural reinforcement? Was the stable rotation state a coincidence of past torques or the outcome of active control? Did the Jupiter encounter play out under the exclusive guidance of gravity and random jets, or did it include an element of deliberate steering? None of these questions has a definitive answer yet. What 3I Atlas has already accomplished, however, is to change the framework within which such questions are asked. It has shown that interstellar visitors can be rich in volatiles on scales meaningful for propulsion, that their trajectories can be well aligned with planetary planes, and that their internal compositions can depart from local norms. It has provided a concrete example of an object that sits at the boundary between natural complexity and plausible engineering. In doing so, it has drawn the attention of instruments, such as the James Webb Space Telescope, not only as a target of astrophysical interest, but also as a possible technological artifact. That attention, in turn, has sharpened methods and expectations that will be applied to future interstellar travelers. As this particular object fades into the distance beyond Jupiter and toward the outer reaches of the solar system, its legacy within human science will not be a settled conclusion about its nature, but a revised sense of what to look for in the sky. The hydrogen plume, the alignment, the rotation, the composition, and the upcoming tests near major planets form a narrative that will be echoed whenever another visitor on a hyperbolic path is discovered. 3. iAtlas has transformed a category from a curiosity into a field of study. Whether natural or engineered, silent or guided, it has demonstrated that the space between stars is not empty of structure or opportunity. It has shown that the galaxy is threaded with bodies that can serve as messengers, vehicles, or both. The question of which of these roles, if any, this particular object fulfills remains open, and that open space is where the mystery of 3i Atlas continues to reside, even as its physical form moves beyond easy reach of the instruments that first revealed its surprising behavior.